Welcome to today's video where we're going to be looking at this device, our new three-phase voltage sensor, which is there for looking at three-phase voltage measurements, and we're going to be placing a particular emphasis on the distribution cabinets and how this fits in that environment. A little piece of housekeeping before we carry on. This video has already been recorded in German, so if you're looking for that version, please head to our media library on our website or to our YouTube channel where you can find that version of the video. This is for our international audience. So with no further ado, let's go into what we're going to cover today. So we're going to be, first of all, looking at SMIGHT in general, just a quick recap of what we provide. I mean, if you're familiar with SMIGHT, or if you watched one of our previous videos, then you can feel free to skip ahead through this section. There's nothing new there. And then I want to look at why do we even want to measure all three voltages. So we come from a world where we've previously only been measuring one voltage. So why is the change there and where does it come from? After that, we'll have a look at the device itself and what it does, how it works. Then I want to show you how the data that we capture through the device is captured and represented within our SMIGHT IQ cockpit. And then as soon as we're talking about the topic of voltage, the topic of power quality also comes up. So I want to have a little look at how we look at this topic of power quality within our environment, because it's a little bit different than the typical way of looking at it. And just before the end, I'm going to then cover how we can think about in the future dynamic voltage control in the distribution grid. And then finally, what I brought along is a few of the questions that we got in the German version of this webinar, as they may be questions that members of this audience have. Okay, so let's dive into a quick overview of SMIGHT. So as a history, we were born out of a collaboration with Netzebv, which is one of the larger network operators in Germany. They really came with the requirement of, we've got 25 to 30,000 secondary substations that need digitizing to be able to cope with the energy transition. Could you guys build something for us? And out of that collaboration came the products which we now sell today. So we really come from a background within the distribution grid, within a DSO context, and we brought all the IoT know-how on top of that. So we kind of balance these two sides of understanding what network operators need, but also understanding the technical requirements to operate an IoT chain. As a business, we've got over 130 network operators who are already using our technology. At the moment, it's about 5,000 substations, about 40,000 feeders, which are being monitored live every second of every day at the moment. And that's really there just to show that this isn't a nice kind of idea. This is something that's being used by a number of network operators at scale in all kinds of different situations. We have customers who are large cities, we have large regional operators, but equally we have whether it's small towns and villages also using our system. So it's used in a number of different contexts, in a number of different ways by different network operators. And more recently, we got our ISO 27001 certification, and that's really just to give you the peace of mind that the product that you're using, the services that we provide, are always built and run with cybersecurity in mind and to the highest standard. So the starting point for our product range has always been feeder level monitoring, and so we have our sensors, which we usually connect to the low voltage feeders, whether that's in a secondary substation or distribution cabinet. So we're connecting onto the three power phases, but also the neutral line. And from those sensors, we're capturing the current information. So the current magnitude, the flow direction, and the phase angle. Taking that data, then transmitting it via Bluetooth up into our gateway. Our gateway then takes a single phase voltage measurement. So again, that's quite important for today's talk because we're talking about three-phase monitoring. And to give you a bit of a background as to why that was the case is that when you're taking a measurement in a secondary substation, the voltage across the phases tends to be quite even because it's dictated primarily from the medium voltage side. And as you'll see later on, we're now looking at taking measurements further out in the network where that's no longer the case. So that's where we come from, taking a single voltage measurement with the gateway, the current measurements from our sensors, packaging that data up, sending it up into the cloud via mobile networks. And then from there, we offer our own visualization to be able to use the data straight away, but also an API for the data to be able to go out into other people's systems, whether that's a digital twin or a simulation package. The data is not locked up in our system, it's available to be used elsewhere. Now on this diagram, we always make the point that we have the arrows going in the other direction as well. Now that's very important because it symbolises an important difference from SMIGHT to other systems, is that we offer this as a complete managed package. So all of the security updates, monitoring of the devices and validation of data and so on is all provided by us. So you can always be sure that when you install the devices they work and that they're continually being monitored and kept up to date. That's really important because once you have a system like this out in the field, maybe it works on day one, but it's important that it also works into the future. And for that, you need to have this ability to update devices and keep on top of all of the requirements that brings with it. So the way we tend to think about our product range is to think about the first layer being capturing data. So that's where all our sensors lie, and the three-phase voltage sensor sits within this layer on our system. So providing devices which are easy to install, that are always working, and all the communication channels that are around that for that to be able to work. Now data by itself is no use. We don't want data just sitting in servers not doing anything. So we've always placed a great emphasis on being able to make that data visualized, make it usable, so that there's actually value derived from the data. And so through the systems and the services that we provide, we go around this circle with most of our customers. So when you implement solutions like this, you'll first of all start to discover critical points in your network. So from a kind of black box situation before, you don't really know what's happening where, to a situation where you start to understand what's happening. From there, you very quickly move into a case of, okay, I've found critical points on my network, but you've probably also established where you have headroom, where you have capacity in your network. And so bringing those two things together, you can start to use that extra capacity to help support where you maybe don't have as much capacity. So a very simple example of that is one feeder is overloaded, another one's got plenty of capacity on it. Either through a switching action or laying a short piece of cable, you might be able to share the load onto another feeder, thereby using the capacity that you already have in your grid and not having to invest in further infrastructure. But at some point, that need for investment is going to come. It will either be there already or it will come after you've gone through that utilization process, and you'll need to perform reinforcements in your grid. And so here we can help by trying to identify where does it make the most sense to invest first. Also timeline, is it best to do it now or can you delay for another few years, so that you can replan and reprioritize your investment plan. And the next stage after that is to really take the grid models that you maybe already have and start to feed them with this much more rich data as it becomes available from our system, which can then bring you around into the starting point again. Through feeding that model with better data, you can better understand where you may have other critical points in your network, where you have other capacities that you can therefore use, and also how to think about your upgrades. So you can see this going around in a virtuous circle of being able to understand what's happening in your grid. Now, once you come from a point of capturing data, understanding it, the final point which we're starting to see implemented is control within the grid. Now, this is done in very different ways in different countries. In Germany, there's a very kind of clear path to this. The network operators are allowed to dim down loads on the grid if they have a critical situation. So we serve that process in Germany. But in other markets, this may be solved through flexibility marketplaces, such as in Norway. And we can also serve that. So this idea of, I've identified where I have a critical point in my network, and maybe the solution for that, rather than building out the grid, is actually to offer a flexibility service into the grid through the users out there. But you need to be able to identify where, when, and to what extent that's happening to be able to activate it. So let's go back to this question, why look at voltage sensing, or three-phase voltage sensing even? So the biggest driver for us has been the solar build-out. So Germany's been known as one of the leading markets for rooftop solar build-out, and this has created a very particular issue. So it can create a load issue because you have all of the panels coming online and producing electricity at a similar time of day, and that can certainly add up at the substation. That's something that we already measure with our devices, but it comes with a second problem, and that's one of voltage rising. So for those who are maybe not in on the topic, why would it affect voltage? We have to bear in mind that for a solar panel to be able to feed its electricity into the grid, it needs to raise its voltage above that of the grid for it to actually flow into the grid. So if you think of that in the old kind of water example where you say I've got the mains pipe in the street that has a certain water pressure. If I want to take water out of my rain water butt into the street and I just connect it with the hose, the pressure in the pipe in the street will push the water back up into my water butt. That's not what I want. So I have to put a pump in there, and the pump has to have a higher pressure than that in the street if I want the water to flow into the street. And it's exactly the same with the electricity. The inverter has to raise its voltage up above that in the street to be able to kind of push the electricity into the grid. Now this happens piece for piece all the way down the line. So the first house has to raise its voltage a little bit to be able to feed in, and then the next house has to raise it a little bit further and a little bit further. So where this issue presents is down at the end of the line. So it's not at the beginning where we tend to take our measurements in the substation. It's down at the last house or the last distribution cabinet where you're going to see the extent of this voltage rise. And so that's the main reason why we've been wanting to introduce this product, is so that our network operators can then see what is the extent of that voltage increase on the line, and I need to be able to measure it as far out into the network as possible. Now this isn't just a voltage rise problem, there's also voltage drops, and it happens in exactly the same way. And if you imagine lots of EVs charging or lots of heat pumps running, each one incrementally drops the voltage along the line. So at the very furthest point in the grid, that's where it's most interesting to look at what the situation is. So you might think, okay, I don't need this because I don't have much solar in my grid. But if you do have quite a lot of, say, winter load in your grid, then this equally could be an issue that you might see in terms of voltage drops. But the important thing is I want to measure it at the end of the line. And also because houses are connected in different ways, I want to look at it across all three phases, because I may have a particular imbalance that I need to take into account. So that's really where we've been coming from for this. So let's look at the product itself. So I have one here with me today. For those of you who are familiar with our power supply for our flex sensor, it's about the same size in terms of the box here, and also the Conlox connections that we have there are also very much the same. The biggest difference here is that we have 3 of the power connections, whereas you'd normally only have 1 for the power supply version. I've got up on the slide here the key technical data. I'm not going to go through all of those here, but just a couple that are worth mentioning. First of all is the measurement accuracy, which is at 0.5%. That's a difference from our standard system at 3%, because here, where we're measuring voltage for the purpose of measuring voltage, not for the purpose of phase angle calculations, it's much more important to have that higher degree of accuracy. And the other one, just to point out here, was we're measuring the voltage between the live and the neutral, but also between the live phases. We're also picking up frequency, the total harmonic distortion, and also the phase angle between the voltage phases. So those are the kind of key metrics that we're measuring as a device, and kind of comes with the name on the tin. It's a voltage sensor. Now it's not only a voltage sensor, so we've also built in the power supply capabilities into the device. So if you're using or planning to use our flex sensor, this can power the flex sensors, but it can also power our gateway. And that was a very conscious decision, because when we install our gateways within secondary substations, we've usually got a power socket. So it's a very simple installation. You just take the plug and put it in the socket. And even if there isn't one, there's usually space, and it's quite common to be able to put an additional plug socket in there. But when we're talking about installing these further out into the grid, we're talking about distribution cabinets, and there's probably not a socket, and setting one up there is much more difficult. So we wanted to make it super easy for our customers to be able to power the gateways as well. So you can not only power the flex sensors, but you can also power the gateway with this device. So you have everything all in one from the one device. I now want to show you a quick installation video where my colleague can show you how these are installed. And again, we've tried to keep the SMIGHT concept of making things super easy to be able to install out in the field. Okay, so now we've looked at how easy it is to install. Once it's out there and installed, now let's look at what the data then looks like. Okay, and here you see our SMIGHT cockpit. The core idea with our SMIGHT cockpit is to give you a good, quick overview over your grid so that you can hone in on the critical points within your network. So the primary way in which we do this is by showing all the points where we're taking measurements on a map. And so you can see these pins. Each one of these pins represents where a gateway is installed. So it could be a secondary substation or a distribution cabinet. And then through the color scheme, we're picking out where you have critical events where 80% of the threshold, whatever that might be, it might be a current based on a fuse rating, it could be a power level based on power settings, but it could also, in the case of what we're talking about today, it could be a voltage violation. So if I've got anything within 80% of the allowable levels, I'd see it in red. If it's between 60 and 80%, you'd see it in yellow. And if it's within 60 to the norm, then it will be green. So from there, I can then start to find out where the issues are. So if I look here at this one, and you can access all of this online, so if you want to look at it for yourself, the best example of this is in the demo ZKM one, which is the pin in the middle of the map. If I go into there, now this is a representation of a distribution cabinet. So one of the key ways of being able to see that that's the case is that within a substation you'd see also transformers at the top on the left here. But we don't see that, we just see a distribution panel. That's quite what we'd expect. And then over here on the side we can see here we have 3 voltages. So if I'm only interested in one particular one, I can filter those in and out. That's absolutely fine. But because we've got all 3, you probably want to see all 3. And then in the typical SMIGHT way, if you've got something of interest, you can zoom in time-wise very easily by highlighting the area. So I've got a notification here that I've gone over a threshold. I might want to look at that in more detail. And each time I do this, I'm going down and down within time spectrum down to the single 1 minute values. Now, yes, it's one particular phase that's gone over, but looking at this data, it's not as if I have a particular phase problem. I mean, all of the phases in this case are quite close to that threshold limit, so I might want to look at what I might be able to do about that, but you could equally have one phase that's going over the threshold when the others aren't, and therefore there may be a different solution. But you can see how you can go from an overview of your grid to be able to identify critical points and then go down into the detail as to what's driving that. Okay, so I hope I've been able to show you how you can quickly get an overview of the data, and it's easy to interpret. That's always, again, the SMIGHT concept that we have, is to be able to quickly get an easy overview of the data, not complicating things, so you can see what's important. So having looked at how we represent the data, and I want to look at the topic of power quality, because as soon as you're measuring voltage, power quality is an important topic that always comes up. So first of all, we need to understand the 2 standards which really make up power quality as a topic. So on the one hand, we have the EN 50106. That is the standard which dictates what the limits are. And then on the other side, we have the IEC 61000-4-30, and that tells you how the measurements are made. So those 2 go together to say, what is it that we need to measure, and what are the limits defined as, and how should the measurements be taken? So those 2 things go hand in hand. Now from the one side, we're not measuring all of the things that are in EN 50106. That we're just taking out the ones that we believe are useful. And then on the how are they measured, we have a Class S device. So it is taking the measurements at that level, but it's only the measurements that we believe are relevant. And so the way to think about this is you can get out in the market at the moment a power quality analyzer. That takes all of the things that you need to measure, measures them in a particular way, either a Class A or Class S, and they have a full power quality analysis. The way to think about what we're offering is a power quality indicator. So we're taking particular values that we believe are important, we're measuring them accurately, and then we're trying to represent them in an easy to use way. So to give you an indication where you have a power quality issue, as opposed to giving you a full power quality analysis. And so what we envisage doing is what we have up on the screen here, where you might have a traffic light system for some of those parameters. So for instance, the total harmonic distortion, do you have it all in the green zone, or are you starting to see a level that's getting towards the limits? That would be, then you get the amber alert, and then if it's over those limits, then maybe you get a red alert. So trying to make it super simple and super easy. So the final main topic that I wanted to cover today is the concept of dynamic voltage control. So where we've already been doing this with our customers, you always get into the situation of saying, great, now I can measure where I have the issue, but what do I do about it? So when I establish that I have a voltage level that's too high or too low in part of my grid, what tools do I have to actually be able to address that, other than having to do a full reinforcement of the network in some way? And so we'd like to think about the idea of dynamic voltage control, where we can take those signals and have a live reaction in the system. So we have our sensor, which is installed in the distribution cabinet, have that data going live up into the cloud. Now we can send two types of signal. Now one option would be to get a voltage regulator and install that in the feeder. So that's the box that I have here. It's again about the size of a distribution cabinet. You can install this usually about halfway along the line, and that can change the voltage in the line. So in the situation where I have a particularly high voltage at the end, I can have the voltage steadily going up. The voltage regulator drops it at that point on the feeder, and then it can continue going up from there. So the whole line remains in the window that you want it to remain in by dropping it at a strategic point. And exactly the same the other way around. If I have a voltage drop, the voltage will be going down. At that point in the network, I can then raise it back up again and then let it go down so that the whole line stays within that window that you want it to stay within. And that could be dynamically controlled. So rather than just have it drop it all the time, you could then have a problem from season to season, or different types of day or day and night situations where you're overcompensating in one direction or the other because you have lots of solar input during the day but lots of EVs charging at night, let's say. Then you could really come into problems of overcompensating in the wrong direction. But by taking a live measurement and putting that into the voltage controller, you can then actively control that voltage according to what's actually happening. And it may just be a temporary measure. You may say, I need to install that now for the next 2, 3, 4, 5 years until I perform some other form of network upgrade, so maybe laying a different cable in the street. But these can be taken out and placed somewhere else in your network. So you could strategically place these where you have issues, have them dynamically controlled, and move them through your network as you steadily evolve. And then the other direction that this could work in is actually direct control at the house. So when we've got that solar feed in, a lot of inverters these days can actually control what they feed in, either in terms of the reactive power that they're feeding in, but also just in terms of the amount of load. So by sending a signal to the inverters, you could actually get these solar systems that are causing the problem to actually adapt their behavior, and again, live to what's happening, rather than just telling them all, I don't know, around midday to all drop down. That may not be necessary on that particular day, that you can do that in a dynamic way. And that's all possible through the structures that we have in place today. So being able to identify what's happening, where it's happening, and have the communication channels out into the outside world for other devices to be able to react to. So we really can create a kind of a smart grid of the future really today. That is possible. And then finally, a few of the questions that we had in the German version of this webinar. And the first question that came up was, how many sensors can the voltage sensor supply power to? So this is referring to our flex sensors, where previously we had a power supply which was separate. And as before, the power supply component of this can supply 20 sensors. And why 20? Well, that's the maximum number that our gateway can connect to at one time. So we've obviously matched it to that so that everything can work as planned. Then the next question was, why do you still use Bluetooth to transmit the data when you've now effectively got a wired connection? So what this question was really oriented around is that under our standard setup, we have the current sensors communicating their data via Bluetooth to the gateway. And now, if you think about it, if you have the flex sensors connected to this as a power supply, and then this connected as a power supply to the gateway, you've now got a wired channel. So why bother with the Bluetooth? It's a fair question. And the reason why we've kept it this way is for intercompatibility. So we have customers out there who are using some mixture of our devices already, and we don't want them to not be able to use their current devices. So that's one reason for it. But it's also, our overall concept is to have a flexible installation, and the wireless connectivity is a key component of that. So to make sure that all of our different devices continue to interact with each other and you continue to have the flexibility with all of the different devices, we've kept that Bluetooth connection as being a key component of that. The next question we got was why only 50 degrees for the ambient temperature and not 70? Again, this is a very fair question. So if we look at some of the tenders and other specifications that we see out there, very often 70 degrees is set as the requirements for some of these devices. And really this is driven by our need to promise a certain level of longevity for the devices. So there's some components within the device which can have accelerated aging at 70 degrees. And so to be able to give the shelf life, or the usable life rather, of the devices, we have to set that at 50. That doesn't mean that if it were to suddenly go over 50 or be at 70 degrees, that the device would suddenly stop working. That's not the case. We've got the same components in many of our devices today, and they don't suddenly drop out at that thing. It's just that the total usable life is shortened to some degree. We don't know exactly what that degree is. We test to 50 degrees to ensure that we can give that product life at that temperature. And the other thing to note is that 70 degrees is often mentioned, but the reality is somewhat different. So even when you have a distribution cabinet in the middle of the summer, in the sun, and you've got lots of current flowing, so the fuses might be hot. Yes, it's very hot in there, but heat rises, and all of our devices are installed down in the base of the distribution cabinet where it's much cooler. And so the actual measurements that have been taken in studies of this type have shown that in the area where we're installed, you don't tend to get above 50 degrees even in extreme situations. So it's maybe a bit of a nuanced answer, but that's really the reasoning behind it. Then we had a question about, are the Conlocks connectors, that's these devices, about whether they're designed for multiple use. And again, we need a bit of a nuanced answer to that one. So yes, they're designed for multiple use, but it depends on what your definition of multiple use is. So our system in general is designed to be flexible, but not mobile. So it's not something that you would install 1 week in one place, take it out, and the next week in another, and so on and so forth. It's designed that you can install it. You probably install it for at least a year somewhere, because you need to see the full seasonal demand change. And then you might establish that that particular area of the network, nothing of any interest is happening, or maybe you've performed some upgrades and therefore everything's absolutely fine and therefore you don't need to monitor it anymore. You can then take the device out and move it somewhere else. So at that kind of frequency of every few years, I might be taking the odd device from one place to another, absolutely. But the other thing that's important to mention, that should you move it around quite a lot, these pieces themselves can be exchanged. So I can put a screwdriver in the top here, and there's a spring mechanism where I can open this and take it off, and that can then be replaced with another one. And these pieces are not that expensive. So should you end up moving around your devices more often, or if one of those were to break, you haven't lost the whole device, you don't need to rewire it. It's simply a case of putting a new connector on the end, and that's a fairly simple and inexpensive thing to do. Okay, and that brings us to the end of this video. So for further actions, you can go to our website where you can find more information about our voltage sensor, but also all of our other products. We have our newsletter, which you can sign up to, which we send out from time to time with product updates and other information. We have our LinkedIn page, which is also a good place to keep up to date with what we do. And then if you like videos like this, we have our YouTube channel, but also the media section of our website where we have all of our product videos, webinars and other information. And of course, if you want to get in contact, we have our contact section on our website, but also the details that you see here on the slide. Thank you very much for watching, and we look forward to hearing from you.